All right, so let's talk about limits. You're like, what's a limit? Let's look at the English definition of a limit. I went to the dictionary and this is what I found. The definition of a limit, according to the dictionary, says it's the final, utmost, or furthest boundary or point. So notice something. The definition in our dictionary about a limit is it could be the furthest boundary or a point. Okay? Mathematically speaking, the definition of a limit reads like this. As x approaches a, the limit of f of x is L, and it's written as, so let's write it. It would be the limit as x approaches a of f of x, some function, is L. You're like, okay, what the heck? I get it. But let me go back a second, and I haven't even read down here yet, so just hang in there. X approaches A. Here's how you write x approaches A. So something I'd like you to actually see from here. X is usually in the domain, correct? Approaching A. A must also be a value of x. It must also be in the domain if x is approaching this number. A must also be a value of x. It must also be in the domain. Now here's what I need you to understand. It's approaching A. It may never get to A, but it's getting close to whatever that x value is. All right? The function f of x, okay? So I'm taking the limit of this function as x is getting closer to this other x value known as A. And it finally is equal to L. Now, L, here's a question. Would L be considered an x value, or do you think L would actually be considered a y value? Here's your x's, and they're getting to this other x value. And that other x value is not necessarily getting into this, plugged into this function, but you're looking at this function based upon this x. This result then, this L, must be a y value. It must be part of the range. Okay? So your A is part of the domain. It's an x value when you're graphing. This L is the output. It must be part of the range, a y value when you're graphing. Okay? Let me continue with the definition. So, as x approaches A, the limit of f of x is L. If all values of f of x are close to L, f of x is another notation for y, isn't it? So this is representing a y, isn't it? So if all values of f of x or y are close to L, which then must also be a y, just like we discussed up here. For all values of x that are sufficiently close to, but not necessarily equal to A. So these two guys are part of the range when you're looking at a graph. This value of x and this value of A must be part of the domain. Notice it says sufficiently close to, but not necessarily equal to that A, that x value. The limit L, if it actually exists, because sometimes it doesn't, and don't worry about when it does, when it doesn't, we'll get there at the right timing. This limit L must be a unique real number. Unique, one of a kind. Real number, no imaginary numbers. Why? Because when we look at this pictorially, we're doing a visual looking at it, which means we would look at a graph sometimes. The graph only has an x and a y axis. There's no imaginary axes here. So the L must be a real number, but it also has to be unique. It has to be one of a kind. You can't have two different L's. Good? Okay. So if you haven't done this yet, pause the video, take time to copy this down, and I am going to see you in a few moments. So let's look at some examples. Remember, the title of this particular lecture says limit. It's a numerical approach as well as a graphical approach. So we're going to look at the numerical approach first, okay? Numerical. So kind of think algebraic, all right? We're going to start over here with these examples, and these examples say fill in the blank. So let's look at the first one. As x approaches, the value of negative 5x approaches 10. You're like, huh? So remember, as x approaches some number. So let me ask you something. This number we're trying to find, does it represent an x or a y? Good, it represents an x, because if x is approaching it, then it has to be a value of x. Then the value of negative 5x has to approach 10. So negative 5x, couldn't that be considered your function? So that's kind of your y, isn't it? And it has to approach 10, doesn't it? All right, so don't think too deep here. What I'd like you to just, in your brain, figure out, hey, what number do you have to plug in for that x that you're going to get 10? And those of us who are very visual should set something up, such as, hey, negative 5x has to equal 10, so what does x have to be? Yeah, x needs to be negative 2, doesn't it? Okay, so here's the deal. The limit as x approaches negative 2 for the function negative 5x is 10. Again, a numerical approach, or algebraic if you want to use that term instead. With me? Don't think too deep on these, all right? Especially when there are algebraic or numerical approaches. Don't think too deep. You know how to do that stuff. Good? Let's look at number 2 on fill in the blank. As x approaches, the value of x minus 3 approaches 7. So the unknown is representing what variable? An x or a y. Good, it's representing x again because x is approaching it. And so x minus 3, what is that considered? Yeah, that's your function, so that's kind of like a y value, isn't it? And so this x minus 3 is approaching 7, and 7, is it an x or a y? Yeah, it's another y value. Okay, so as you work this out numerically or algebraically speaking, you would get x equaling, good, which means the limit as x approaches 10 of the function x minus 3 is equal to 7. Agreed? So my unknown here would be 10. Are you okay with that? Like, that was pretty easy. Is that, you know what? For these problems right now, that is basically it. I need you to think numerically or algebraically when you're looking at these, okay? It's getting you used to this limit. When we look at the graph, it'll be a little bit different, but no worries about that, okay? All right, let's look at over here, this problem. This one's actually asking me to find the limit. Now, it has given me a function, and my function is the absolute value of x. And it says, find the limit of this function as x approaches 0. Well, I'm going to write it as the limit as x approaches 0. What's my function here? Yeah, the absolute value of x. Now here's the deal. I can plug 0 into here, can't I? And say, well, what's the absolute value of 0? Yeah, it's 0, isn't it? So the limit as x approaches 0 for this function is 0, right? You're like, that's it? Yeah, just Algebraically, numerically speaking, yeah, don't think too deep on this, okay? Let's look at this next one. It's part B to problem number 1, which means my function is still the absolute value of x. So I'm going to rewrite it. We have the limit as x approaches -2 of this function, the absolute value of x. What do you think you're going to get as x approaches -2? Yeah, we'll get 2 because the absolute value of -2 is +2, isn't it? In this particular case, right, we can actually plug in these numbers for x, no problem. All right, we can actually plug in the values of x, no problem. Sometimes that happens with a limit, and sometimes it doesn't. But stay tuned. Got to know a couple more of these. Find the limit. All right, so let's look at the second example. My function is x squared minus 5, and it has part A and a part B. So let's look at part A. They're asking us to find the limit of this function as x approaches 0. Well, I can rewrite it. The limit as x approaches 0 of x squared minus 5. Okay, so think about it for a few moments and tell me what you think the answer will be. What'd you get? Good. I heard some of you give me an answer and some of you are like, I'm not quite sure. Well, answer me this. Can I plug 0 into there? Yeah, I can. What would I get? -5. No problem. Remember, some of these are very, very straightforward, so don't think too deep about it. And it'll be more obvious when we look at it as a graph, okay? But for right now, I just need you to look at it algebraically, numerically, okay? How about part B? Same function, the limit of f of x as x approaches -1. So, again, some of us may want to rewrite it of x squared minus 5. Okay, what do you think? What are you going to get? Yeah, you're going to plug that -1 in, aren't you? And the first thing you're going to do after you plug it into the x is square it, which makes it +1 minus 5. Yeah, -4. Are you good with that? Cool. Let's look at this third example. Here's my function, and let's look at the limit. So the limit of this, and again, I'm going to rewrite. So the limit as x approaches 0 of this function 1 over x minus 3. What would I get? What do you think? Yeah, you can plug that in, so you get a -1/3, don't you? Correct? Look at part B. I'm taking the limit as x approaches 3 of this function. What do you get? Oh, a little stumped, huh? Because you're like, wait, what? If you plug it in, you end up with 1 over what? Yeah, 1 over 0. Huh. That's not looking too good, because is 1 over 0 a number? No, what's that word? Ah, yes. This is described as undefined. So when I plug this in, I got an undefined answer, which means could I actually plug 3 into that? Nope. So here's what that means when I get this type of situation, numerically speaking, algebraically speaking. It actually means the limit does not exist, or DNE for short. But in this case, the limit does not exist. How could the limit exist if I end up with an answer that's undefined? That's not something I can graph. That's a hole in the graph, as a matter of fact. Good? Okay, stay tuned. I got another theorem for us. Well, actually, I have our first theorem for us, so stay tuned. So let's take a look at this limit. Or let's take a look at this theorem, which is talking about limits. As x approaches a, the limit of f of x is L. Okay, well, we know that. We've already been working with that. But the next word says if. If requires a condition, at least one condition. if the limit from the left exists and the limit from the right exists and both limits are L. So it's saying the limit of f of x is L if the limit from the left and the limit from the right, if they both exist and they're both actually equal to the same number L. Because remember the definition of limit? L had to be a unique number, a real number and a unique number. So let's look at how this is actually written. It's written as, right, if the limit x is approaching a, and it says if the limit from the left, so here's how I designate that I'm looking at this a, I'm approaching this x called a from the left. The minus sign is like in an exponent position. It's not an exponent, but that's the location it's at, so I know that I'm coming in from the left and approaching this number a of the function. Okay? And this must be equal to the limit as x approaches a, but now it's from the right. So here's still that a, but now I'm coming in from the right, and that's my positive direction, so to speak. Still looking at the same function. So far, so good with me? So, if the limit of the function as you're looking as x approaches from the left equals the limit of the function as x approaches that a from the right, if those two are equal, then, oops, sorry, I kind of forgot to write something. If they both equal L, then I can say the limit as x approaches a. Notice it doesn't say from the left or the right, which means it's encompassing both of them. The limit as you're looking from the left and then you're looking from the right, if they're both approaching that same y value, then the overall limit is that L, is that y value. Good? Stay tuned, I got an example. So let's look at this fourth problem. The directions are still to find the limit. Okay, it's a continuation of those three problems that said find the limit. But I had to throw a theorem in the middle of it. Why? Because if I look at problem number 4, the function they gave me is a piecewise function. Remember that? A piecewise function? It means it's in pieces, and in this case it's in two pieces. The first piece, 2x plus 1, can only be used for x less than 1. The second part of the function, x, can only be used for x being greater than 1. Right? So, let me just kind of draw this out a second. Here is the 1, right? Because that's kind of where it does a break. And for x less than 1, that's all those numbers to the left of it, agreed? My function is the 2x plus 1 function that I'm allowed to use. And if I look at all those numbers to the right of the 1, that's this function, isn't it? That is the x function. And by the way, the x function allows me to actually use the 1 because x is actually equal to 1 down here. Cool? With me? All right. So, I see parts A, B, and C. Let's just go with part A and see what it wants us to do. It wants us to find the limit as x approaches 1 from the left of this function. All right, so I'm trying to find the limit as x approaches 1 from the left. Well, if I look at this visual aid for ourselves, if I look at the number 1 and I'm coming in from the left, the function I'm allowed to use is 2x plus 1, isn't it? Because that's for all that x is less than 1. So I'm actually taking the limit of the function 2x plus 1. And when I do that, I'm still just going to plug the 1 in here. So I get 5, wouldn't I? It's approaching it. You're like, yeah, but you can't let it equal to 1. You're right. I can't let it be equal to 1. But as x is actually approaching the 1 from the left, the y's are going to approach the number 5. Cool? That's what it's telling me. As x is approaching 1, coming in from the left, this is the function I'm going to use, and the y's are going to approach the number 5. Good? Okay. Let's look at this other one. The limit as x approaches 1, now it's from the right. So now I'm coming in from the right. And according to our visual aid here, yeah, the function I'm going to use is x, because x's are, this function x is allowed to be used for all the numbers greater than the 1. So in this particular case, as all these x values are approaching the 1, my y value is going to approach, 1. And it'll actually be equal to 1 because I'm allowed to plug in the value of 1 for this part of the function. Cool? Okay, are we good with the left and the right? If not, back it up. Listen to it again. Cool? Okay, and now part C says, hey, what's the limit of this function as x approaches 1? Remember the theorem we just looked at? If x approaching 1 from the left and x approaching 1 from the right have the exact same limit, then the limit exists. Then that limit would answer this question. But here's what I'm seeing. What I'm seeing is this. The limit as x approaches 1 from the left of this function does not equal the limit as x approaches 1 from the right of that function. They're not equal. This value is a 5. This value is a 1. These guys are not equal. Even though there's a limit from the left and there's a limit for the right, since they're not the exact same number, this answer does not exist. The overall limit for that function as x approaches 1 does not exist because I'm getting two different answers from the left and the right. Cool? Okay. So we just looked at this numerically or algebraically up until this point. We're going to start looking at it graphically. Okay, so as mentioned, we are going to look at finding the limits graphically. So we have this particular graph. It's the graph of a parabola, and it is labeled capital F of x. And they're asking us to find the limit as x approaches -1. So in order for the limit to exist, as we looked at a theorem just a few minutes ago, we have to make sure that the limit as we come in from the left and the limit as we come in from the right match. If they don't match, the limit doesn't exist. So let's take a look at this. When we come in from the left, that means we're going to be coming in from this direction on the graph. So we are going to just travel on the graph along from the left until we get to -1. So we end up at that open circle. Now that we've done that from the left, we're going to come in from the right and we're going to start on the graph over here and move our way down until we get to -1. So both places, if you notice, are meeting right here at this open circle. That open circle is the point 0, -1. Let's see if I can write that a little bit better for us, shall we? That open circle is 0, -1. Now remember, the limit means that when I come in from the left and I come in from the right, the y value that they're ending up at is the same. And since coming in from the left and coming in from the right, they both end up at that same point, 0, -1, The limit does exist. And some of you may be thinking, wait, that's an open circle. How could that exist? It's not asking for what the y value is when x equals -1. I'm not working on x equals -1. I'm working on what is the y value as x approaches -1. As x approaches -1 from the left and the right, the y value they're approaching is -1. So the limit is -1. Pardon me. Let's try that again. The y value is 0. And I even wrote this point incorrectly, didn't I? Boy, I hope you guys out there are paying attention to how I wrote things, right? The point was -1, 0. My apologies, I'm so sorry. So anyway, you guys with me? Okay, let's look at another graph. This is a very interesting graph, is it not? And it is called the function capital F, once again, as it says in the first part of the directions. And they are asking us to find the limit as x approaches -4. So -4 is right about there. So when I come in from the left and I come in from the right, my graph coming in from the left and coming in from the right need to approach the same y value in order for there to be a limit. So we are going to start coming in from the left, and this will be the graph that we're actually going to travel on from the left. So we're traveling along, and we end up at that closed circle, don't we? And now I am going to come in from the right, and here is the graph for me to travel upon on the right, coming in from the right, and I end up at that open circle. So here's the deal. When I come in from the left and I come in from the right, they're not meeting at the same point, are they? They're meeting at two different, they're not even meeting. They're going to two different points, aren't they? They're both heading to -4, but they're both heading to two completely different points. So if they're heading to two completely different points, are they heading to the same y value? Nope, you're right, they're not. So if they're not heading to the same y value, is there a limit? Correct, there's not. The limit will not exist in this particular case. With me? Okay, let's look at another graph. They say this is the graph of G. Again, it's a very interesting graph, but don't look at the graph as a whole. Let's look at what they're asking us for. Now, notice something in this particular case. They're asking us to look at this graph, but as x approaches what number? Remember that little negative in the exponent? What does that mean? Yeah, come in from the left. So we're actually approaching what number? Good, we're approaching the 1, and we're approaching it from the left. I don't care about the right side at all. All I care about is the left side. So I am going to travel on this graph from the left, and as I travel on this graph from the left side, and I approach +1, I end up at that point, don't I? Now, that point is the point 1, 6, isn't it? Now, here's the deal. Since it comes in from the left only, do I care what's happening over here on the right? Do I care where it's approaching? Nope, I could care less. By the way, do I care about x actually equaling 1? I don't care about that one either. All I care about is what happens as as my graph is approaching 1 on the x's. What y value are we heading to? So what do you guys say? Yes, we're heading to 6. I don't care about x equals 1. That would be where that point is. But that's not what it's asking. It's where is it approaching? Are we good? Okay, let's try another one. Another interesting graph. Agreed? They're calling it capital G. Again, let's take a look. What are they looking for? They're looking for where x approaches 3. Well, 3, I should say, on the x's is right there, isn't it? Now, it didn't have a little plus sign or negative sign in that exponent of 3, which means I'm looking to see if the limit from the left and the limit from the right, if they're going to the same place. If they're going to the same place, we have a limit. If they're going to two different points, then I don't have a limit. So let's check out from the left first, which means I'm going to travel along here, and I end up at this open circle. And now let's see what happens as we approach from the right. Here's my graph as we're approaching from the right, and I end up down here at this open circle. So as I come in from the left, I'm up here. As I come in from the right, I'm down here. Did they meet? Nope. So is there a limit? Nope. So in this case, the limit does not exist. And some of you are going, hey, wait. What about that closed circle right there? Well, you know what? That closed circle is where x actually equals 3. And that was not their question. Their question was not x equaling 3. Their question was, what happens as we approach 3 from the left and the right? As we approach it from the left, it's up here. As we approach it from the right, it's down here. So no, they're not meeting. No limit. Got it? Okay, let's check out another one. Here's an interesting graph, right? And they're calling it little f. And they're asking us for the limit as x approaches 3. And again, it doesn't have a little plus or negative sign up there. So that means I have to come in from the left and I have to come in from the right and see what's happening with the graph. Agreed? All right, so we're going to check out coming in from the left first. Now you're like, well, which one of these do I look at on the left? Well, if I look at this one kind of stops here at the -4 on the axis. I need to go all the way to the 3, which is right here. So this graph isn't even heading towards the x equals 3, or x approaching x is 3. Not equal, but approaching x is 3. Now, this graph right here, if I take a look at this graph right here, this graph isn't heading towards, from the left, isn't heading towards x being 3 either. This one is kind of going just towards where x is 1, which means this isn't the graph I'm going to look at either coming in from the left. The graph I'm actually going to look at in this case when I'm coming in from the left is this one. Here's where I'm actually going to start. I am going to go here, and as I come into x approaching 3, this is the graph I'm going to look at from the left. And when I'm looking from the right, this one was a little more obvious as I'm looking from the right, and we're approaching right there, aren't we? So from the left and from the right, they're both approaching that same point, aren't they? And that looks like the point 3, 0. So when they approach from the left and they approach from the right, they're both approaching that exact same point. So do I have a limit? Yes, I do. And what's our limit? Good, 0 in this case. Agreed? Remember, the limit is the y value. What y value are we approaching when we approach this x, as we approach this 3 on the x-axis? Cool? How we doing? Okay, no surprise, got another one for you. A very interesting graph, isn't it? Okay, so let's check it out. There at that graph is called f of x, little f of x. And they're asking us to find the limit of it as x approaches 5. So there's no plus sign or minus sign in the exponent position on the 5, which means I got to look at it from the left and I have to look at it from the right. And I have to choose the correct graphs to actually look at. So this little graph right here, does that graph head towards x being a positive 5? Nope. Not using this one. Forget it. this graph. Now, when I look at it, this graph actually does approach x being 5, because here's the 5 right here, this like line right there. So it does actually approach it. So I'm going to use that graph to look from the left as x approaches 5. And since there's no solid circle up there, that tells me that that graph is heading towards positive infinity. Good? Makes sense? Okay, then I am going to look from the right, and this is obviously the graph from the right as it approaches 5, and so now, there's no solid dot down here either, which means it keeps going. So, since there's no solid dot there, it looks to me like this one is heading towards negative infinity. So if I've got one part of it heading towards positive infinity, the other one heading towards negative infinity, are they heading towards the same y value? No, they're not. So if they're not heading towards the same y value, then guess what? Yep, you said it. Limit doesn't exist. Good? Making sense? Okay, got one more for us. So let's take a look at this one. Same thing. Here's a graph. Now, this one is interesting on their question. Look at their question. As x approaches infinity. So infinity is out here somewhere, isn't it? Right? For the x's, as x approaches infinity. Well, I still have to come in from the left, and I still have to come in from the right and see what's happening. With me? All right. So, x approaching infinity. Is this graph using x approaching infinity? No, as a matter of fact, it looks like this graph has approaching -2. So we're not using that one. This second graph right here, is this one where x is approaching infinity? Nope, doesn't look like it either. So forget that. Are you with me? So it looks like we are going to be focusing on this graph. And from the left, when I'm going to x infinity, it's heading in that direction, isn't it? Agreed? Okay, so you're like, well, what about coming in from the right? Well, this one is interesting because to come in from the right, you can't really come in from the right to approach infinity for the x. So we just keep going out in this direction. Now, I'm going to erase that line because I need you to see what that really looks like. This graph, as we follow it and it approaches infinity on the x's, which means it keeps going out here, do you notice it doesn't go above the x-axis? It is just underneath the x-axis, isn't it? It's just almost ready to hit the x-axis, isn't it? Well, if it's ready to hit the x-axis, that means the x value is whatever the x is. But what's the y value going to be as it's just skimming underneath the x-axis? Yeah, that y coordinate is 0. It's almost like we're hitting x-intercepts. So in this particular case, your limit for the function will be 0. Good? Does that make sense? Okay, so as always, I recommend reviewing this, going back, rewinding it to make sure you understand it. And I'm going to say you guys have fun with limits, and I'll catch you on the flip side.